Hey, welcome back. So we are ready for our next piece of our chemistry puzzle, which is nice. I do appreciate in chemistry that the things we have learned, we continue to use and build upon, which is great because it's like, oh, we really did need to know how to do this stuff so that we can use it for something new. And so now that we know how to balance our chemical reactions, the question is, what can we do with that information? So let's take a look at what it is we're really describing when we balance something. So let's say we had some hydrogen particles, H2. These are gas. We've actually seen this reaction before, I think. They will react with some oxygen gas particles and they'll form some water, right? Usually in the form of vapor or liquid if you give it enough time to recondense or if you make enough of it. Anyway, and so here we've got a chemical equation, a chemical reaction, but there's a problem. Law of conservation of mass says you cannot create or destroy matter. We need to balance our oxygens. We had 2 here. Now we've got 2 oxygens there. Awesome. And now we've got 4 hydrogens. So we're going to need a 2 over here to balance our hydrogens. Cool. Hopefully you're at this stage of the game. Oops. I want to keep the 2 there. At this stage of the game, hopefully you're feeling pretty good on how we start to balance our chemical equations. Now, what do these numbers actually mean? Well, for this, it means that in order for this reaction to go, I would need 2, I'm going to shade them here. I would need 2 molecules of hydrogen for every, let me change my color here. For every 1 molecule of oxygen, right? So 2 hydrogens react with 1 oxygen. And if we do that, we can end up making 2 molecules worth, 2 molecules worth of water. So we've got these coefficients that are really describing how many particles are interacting in the reaction. But we can take it a step further, right? Well, what if I doubled the amount of hydrogen? What if I had 4 hydrogens, right? I actually had 4 hydrogens. If I had 4 hydrogens here, well, and then I use, I don't know, I can double my oxygen, right? Because that's pretty abundant. Well, if I had 4 moles or 4 particles of hydrogen and 2 particles of oxygen, well, wouldn't I be able to double the amount of hydrogen that I get? And the reason this becomes important is because it turns out our ratio is just that. It's a proportion. For every 2 of these, I need 1 of these to make 2 of these. If I had 4 of these and 2 of these, I could make 4 waters. Well, what if I had 6.02 times 10 to the 23rd hydrogens? Oh, okay. We could actually use our mole values. And this is really what we've been building to. These coefficients provide us a ratio. They tell us the proportion or the recipe that we need to follow to make it work. But we can also use those to predict or determine, based on the amounts we're using, how much product we would expect to see or how much we would need for the reaction to go. Let me show you an example. Hopefully it'll make sense as we go here. And I'll try to color code here as we go as well, just to make sure our values are easy to track. Cool, so let's take a look at 8.8. Now we talked about this idea of using the coefficients as kind of a ratio or a proportion, because that's really all it's doing for us. But that does mean that whenever we come across these problems, we always got to do our balance first. So for number 1 here, go ahead, take a second, balance it. Hopefully you got 2, 2, and 3 for our balance on our first reaction here. We've actually seen this one before. I think it was on the quiz. Hey, check that out. Cool. So the question goes on to say, in the decomposition of potassium chlorate, how many moles of potassium chloride can be made from 34 moles of potassium chlorate? So this is our potassium chloride with that 8 ending on it, right? Oxygen's on there. Cool. This is a little bit of math, but good news. It's going to be the same type of problems we were seeing before. We're just going to use slightly different conversion factors. We always start with our given, right? Here's our given. We're starting with our 34.0 moles. And now it is really going to matter that we bring our units all the way along, because we're actually going to be changing our moles here. So we know here's how many moles of this stuff we're starting at. We want to figure out how many moles of potassium chloride we can make. We're trying to go from moles of one thing to moles of something else. If you remember, we had that mole train before that kind of helped us out. We're going to make kind of a new one here. If you were given moles of some stuff, I'm going to call them moles of substance A, and you wanted to change it into moles of something else, I'm going to call it moles of substance B. The way we would do that is with what we call our mole ratio. our mole ratio. It's really just going to be the coefficients, and I'll use green for that. Sound fair? So our mole ratio comes from the balanced equation, from the reaction, if you will. And so for this one, we would look, okay, right now we're starting in potassium chloride, right? Nope, potassium chlorate, sorry. We're starting in potassium chlorate. We want to cancel that. So we're going to put moles of potassium chlorate in the bottom. We're trying to get to, sorry, I should color code. I told you I'd color code. No, I didn't. So we're trying to cancel, wrong button again, sorry. Cancel our moles of potassium chlorate. We're trying to get into moles of potassium chloride. Well, that relationship comes from the balanced equation. We know that for every 2 molecules of potassium chlorate, we can make 2 molecules of potassium chloride. Well, then if we had 2 moles worth, which is still just a number, right? An amount, if we had 2 moles worth of potassium chlorate, it would make 2 moles worth of potassium chloride. And I know what you're thinking. You're thinking, Mr. Jorgensen, this seems silly. 2 divided by 2. So here's our 2 moles of potassium chlorate. That's going to be equal to 2 moles of potassium chloride. If I'm looking at my units, my moles of potassium chloride cancel. Now I'm in the unit that I want. But I know what you're thinking. You're like, why would we do this? It's the same. If it's a 2-to-2 ratio, it's the same as saying a 1-to-1 ratio. It's the same number. 34 times 2 is what? 68 divided by 2 is back to 34. Yay! The important piece here is that we changed our units, and it's not always going to be 1-to-1, right? And so we need to kind of spend some time looking at what happens when it's not 1-to-1. Uh-oh, Piscatios, this is out of order from what I've got for you guys today. I apologize. Let me find your number 2 here, and let's take a look at number 2 where it's not going to be quite as clear cut. I sure hope I got the one that we need for number 2. Oh my goodness. Just a second. One more. All right. Sorry about that. I had an old version of the handout pulled up. All right, cool. So number 2. So number 2 is already balanced for us. We're looking at this POCl3 particle decomposing into all of its different elements. Part A says, how many moles of chlorine gas can we make? So our question word here is how many. We're looking for moles of chlorine gas, Cl2, from the decomposition of, here's our given. We've got 0.350 moles of this POCl3. Cool. So I start with given, where we're trying to get to. And now we just need to get from part A to part B. We're going from moles of one thing to moles of something else. To find that relationship, we go to our balanced equation. So here's our POCl3. We're trying to get that to cancel. So for every 2 moles POCl3, we're trying to get into moles of chlorine. Oh, that's carbon. Chlorine, there we go. That's a 3. Ha! So for every 2 moles of POCl3, we can make 3 moles of chlorine gas based on the chemical equation. That's our mole ratio part. And now we just got to solve. So we take our 0.350 times 3, which gives us 1.05 in the numerator. 1 times 2 is 2. So we then divide by 2. Didn't leave myself quite enough room here. So 1.05 divided by 2 gives us a final answer of what do we got here? 0.525 moles of chlorine gas actually being liberated or released in our decomposition of this gas. And so again, just this idea that we can use the balanced equation to change from whatever we're in to whatever we're interested in, because we know the recipe, we know the ratio. One more example for you, and then we'll cut you loose to try number 3. Part B says, how many moles of diatomic phosphorus? So we're trying to find moles of P2 can be obtained in the decomposition of, the same amount. We got 0.350 moles of our POCl3. And again, it's really going to be important that you bring your units. The most common mistake when we start to work these types of problems is folks aren't sure what to put in their mole ratio. They flip-flop the numerator and the denominator. And the easiest way to avoid doing that is to bring your units. We know we're trying to cancel our moles of POCl3. In this case, we're trying to get into moles of our phosphorus, P2. So get your units in the right place. The stuff you want to cancel has to be opposite each other. The stuff you're trying to get into is always going to be on top. And now we can go to our balanced equation and pull our numbers. We know that it's 2 moles of our POCl3 for every 1 mole of P2. That's an implied one, isn't written. So then to solve, really all we got to do is take our 0.350 and divide by 2. This comes out to 0.175 moles of P2. Quick double check on sig figs. This had 1, 2, 3 sig figs, 1, 2, 3 sig figs. Here's our final answer then for letter B. Cool. Hopefully this is helping you start to think about how we can go from moles of something to moles of something else. If you would, give number 3 a try, and then we'll come back and be taking questions next time I see you.